Hi, welcome back to math class. Myself, Lieutenant Venkatesh, Assistant Professor in Mathematics, PB Siddhartha College of Arts and Science, Vijayawada. Here, I am discussing about the definition kernel of a homomorphism. If F is a homomorphism of a group capital G into a group G dash, then the set K of all those elements of capital G which are mapped by F onto the identity element E dash of G dash is called the kernel of the homomorphism F. Here F maps G to G dash be a homomorphism. This is the homomorphism. Then the set capital K of all those elements of capital G, we can take any element. Then the set capital G can take any element belongs to capital G which are mapped by F onto the identity element E dash of G dash such that, so here we observe that which are mapped by F. So the image of this element which are mapped means F of X onto the identity element E dash, that is equal to E dash, is called the kernel of the homomorphism F. So this is the condition for kernel of a homomorphism. Finally, take any element. Suppose A belongs to G, such that F of A equals to E dash. Small k belongs to capital G. F of K is equal to E dash. Some element T belongs to capital G such that F of T is equal to E dash. So this is the definition of the kernel of a homomorphism. By using this definition, I will prove one theorem. If F is a homomorphism of a group capital G into a group G dash, then the kernel of F is a normal subgroup of capital G. Here, for our convenience, the kernel of F is denoted by capital K. Capital K means kernel. The set K. Suppose here and G dash be two groups. Given that F maps G to G dash be a homomorphism. In G is one group and G dash is another group. For this, we have to take two identity elements. Let small e be the identity element in capital G, and also E dash be the another identity element in G dash. Therefore, and also take the kernel definition. According to the kernel definition, take one set capital K is equal to ker F. Ker F, the definition is take any elements X belongs to capital G such that F of X is equal to E dash. So here X belongs to G. X is one element in capital G. That element satisfies this condition. Therefore, X is also belongs to ker F. Some T belongs to G. F of T is equals to E dash. Therefore, T belongs to capital K. So, definitely, since let us prove this theorem by steps wise. First condition. Here we prove that the first step is K is any non-empty set. And the second step is K is a subgroup of capital G. And the third step is K is the normal subgroup of capital G. Let us prove this theorem by steps wise. First step, K is a non-empty set. Since f of e is equal to e dash. This is the property of the homomorphism. F of e is equal to e dash. Therefore, e is an identity element, satisfies this condition, kernel definition. Therefore, e belongs to capital K. Therefore, K is a non-empty. K is a non-empty. This is the first step. And the second step, K is a subgroup of capital G. And the second step, K is a subgroup of capital G. To prove that K is a subgroup of capital G. Already we know by previous theorem in subgroups that A comma B belongs to capital G, then A into B inverse is also belongs to capital G. Therefore, capital G is a subgroup of capital G. So here also we can take any two elements K, A comma B belongs to K. So K is the kernel of F. Whenever the two elements belongs to K, the two elements satisfies this condition. F of A is equal to E dash and F of B is equal to B dash. Sorry, E dash. E dash. So A and also A comma B belongs to capital G. By closure law, A into B inverse is also belongs to capital G. Since B belongs to capital G, then that implies B inverse is also belongs to capital G. By closure law condition, here the inverse condition. Now, F of A into B inverse is equals to, since F is a homomorphism, so this can be written as F of A into F of B inverse. That is equal to F of A. F of A is equals to E dash. F of B inverse, that means E dash and whole inverse. Finally, we get A inverse. Therefore, F of A into B inverse is equal to E dash. So A into B inverse is one element, satisfies the definition of the kernel. Therefore, A, B inverse belongs to capital K. Therefore, capital K is a subgroup of capital G. Subgroup of capital G. Finally, we prove K is a normal subgroup of capital G. Already we know the definition of the normal subgroup of capital G. Take one element from capital G, take another element from the subgroup of capital G. The product is also belongs to kernel of the definition. Okay, and now take X belongs to capital G. X belongs to capital G, and also A belongs to K. Therefore, F of one element from capital G, one element from small capital K, and the inverse element from capital G. This product is also, the total product is also belongs to K. Then K is a normal subgroup of capital G. So for this, we have to write this condition. Since F is a homomorphism, then F of X into F of A into F of X inverse. F of X inverse. That is equal to F of F of X into F of A. F of A is equal to identity element E dash and F of X inverse. That is equal to F of X into X inverse. F of A into F of B is equal to F of AB. That is equal to F of E. F of E is equal to E dash. Therefore, F of X A X inverse is equal to E dash. So finally, the product X A X inverse satisfies the kernel definition. Therefore, capital K is a normal subgroup of capital G. Normal subgroup in capital G. Hence proved. Hence proved. This is the way we have to solve any problem or any theorem by using the definition of kernel of a homomorphism. Thank you so much. Have a nice day. If you have any doubts, please call me or WhatsApp me. I will respond immediately. Have a nice day.